in this lecture, we want to just quickly show how you can calculate various statistics in quantum mechanics. It turns out to be rather straightforward now that we understand our states and our operators. So just recall how we do it in kind of ordinary statistics or probability. We want to calculate the expectation value, or just the mean value is often called. Now, in statistics, you often call it EA, the expectation value. Here in quantum mechanics, we're going to use this symbol, the bracket A, bracket like that. And it'll be clear why we do that in a moment. But the definition, recall, to find the mean value was to sum over all possible outcomes, A sub I is one particular outcome of n, and you multiply that by the probability for that the random variable has that value. And you add that up, that's your average. Right? That's basic, simple definition. Now, the question is, how do we do this, say, if we have an object that's in the state psi, we'll just some arbitrary state psi, and we want to know what's the average value of A that this state has. Another way to think about that is if we ran an experiment measuring the basis of A, what would be, and we took all the outcomes of all the possible outcomes of the observable A, what would be the average value? That's what we'd be doing. Well, let's take a look. All we need to do is really translate this. We know how to find the probability, so we just translate it. Let's just do that first. So again, we're going to represent it this way. So now we're taking the average of an operator, A. So we're going to put the caret on top, and we're put the psi there to emphasize that this average depends upon the state. That should be obvious. Now, so we do this, and now all we do is use a Born probability rule. We just substitute the probability that the outcome is AI, and remember how we do that. It's the state psi, and we multiply by the bra for the particular outcome, and we do the modulus square. And we sum over all outcomes. So that's how you do it. Now, it's going to be useful for us to unpack this modulus square as follows, where, remember, all we do is it's the complex conjugate times that, and that just means flipping the bra and the cat around like that, the inner product. And we want to examine this to see if we can express it in a more compact way. Well, we're going to kind of work from the answer backwards. So we want to look at the following form. And again, the AI are the outcomes in the, or the eigenvalues expressed in the basis A. So let's look at this. So what we're going to do is we're going to take our operator and sandwich it between the states psi with a ket and a bra. And to begin, what we're going to do is we're going to insert the identity operator, so on both sides of A. Why? Well, because we want to use the resolution of the identity. So if we do that, recall the resolution of the identity is that if we, I'm going to highlight this, that if we sum over all the basis vectors in this bra-ket manner like this, that's equal to 1, their identity operator. And we do this twice. So this would be the that one, and let's do another one here. This one here, that corresponds to that one. And so we just insert that, and that's just multiplying by 1. That's what we're doing. But notice what it does. It allows us to really express this in a nice, simple way because of the fact that the AI vectors are eigenvectors of A. So this middle expression becomes easy to calculate because the operator A acting on AJ just returns AJ multiplied by the outcome value AJ. So doing that and cleaning up, let's do this slowly. So what I've done here is now, again, acted A onto AJ, pulling out the factor AJ. Remember, we can put that anywhere we want. Acting on AJ here. And we have these guys on the outside. Now, here's the important thing where I'm just going to state this without fact. Well, no, we can go through it. That this product in the middle here, this A, recall this is AI, AJ. This is an orthonormal basis. So this is only non-zero when I is equal to j, and it's equal to 1 in that case. If I and j are different values, it's 0. So that and this is what's called the Kronecker delta. So it's sometimes called IAJ. What that does is that if we sum over, say, j here, we only pick out the values where j is equal to I, and it collapses this sum where this becomes AI is equal to AI, and this becomes AI, this becomes AI, and we simplify it to this because that's what it picks out. It only picks out those when they're the same. And this AJ becomes AI, of course, and we have this here. Now note, we can't use the resolution of identity here because we have this AI sitting out here. Well, that should be an AI there. That's a mistake. It's supposed to be an I there. Now, notice what we have. This is exactly what we had up here. So what it says is that this sandwiching the operator between the state vector gives us the expectation value for that observable in that state. And that's a nice, simple way to express this. Okay. Now, once you have this, this is really kind of the basis of statistics, is getting the expectation value. Now we can calculate other statistics quite easily. So if we want to calculate the square, the expectation of the square of the operator, well, we just take the operator's squared, the operator acting on itself. That's what we do. Sandwich between the size. And from that, we can get other ones. We can go and then we can define the variance in the state psi as this form here times the expectation of A alone, square that. So this is just getting what we had before, discussed earlier. The covariance of two operators now, A, B, would be A acting on B in this way, and then subtracting the products of the expectations of each. And from that, we can get the correlation as this expression here, which we have the covariance defined here, divided by the square root of the variance of the two A and B. And in the cases we're going to talk about, this correlation is what we're going to be we really care about in the experimental settings we'll talk about. But in the cases we're going to be talking about with plus and minus 1 random variables, the variance will be 1, and the covariance will the expectations will be 0. So the correlation will actually just equal that. But we'll get to that later. They'll simplify. So we won't really be dealing with cases here where we have to find the variance and everything. And that's it. So now we're ready to do some analysis with expectation values and look at experiments.